Dear authors, participants, and organizers, I'm so glad to join you in this session from the 14th International Conference on Scalable Uncertainty Management. My name is Nassim Bahri. I'm a PhD student in Business Computing at the Higher Institute of Management of Tunis. Today, I present our work entitled Rule-Based Classification for Evidential Data. This work was written by myself and my supervisors, Dr. Mohamed and Tobji and Professor Boutheina bin Yaghlane. As indicated in the title, our research tackled the problem of associative classification. Indeed, classification is a supervised machine learning process that builds a model from data, called training data. In particular, the associative classifier is a family of classification techniques that use association rules to classify new instances. In the literature, many works treating the field of rule-based classification were proposed. However, most of existing works focus only on perfect databases. In fact, data involved in real-world applications are most of the time imperfect. This imperfection can be expressed either by imprecision, uncertainty, or even inconsistency. From this context, an important question arises: how to consider the data imperfection when dealing with rule-based classification? My presentation agenda is as follows. We start with recalling the basic concepts related to our research area. Then we introduce the problem statement and the proposed approach. Later we present the experiments and we discuss the obtained results. Finally, we conclude this presentation and present further research. So we start with the background material. To handle imperfection in data, many theories were proposed. And one of the most common ones are the evidence theory, also known as the Dempster-Shafer theory or the belief function theory. It was introduced by Dempster in 1967 and then developed by Shafer in 1976. It's also known to be a powerful framework for representing and managing imperfect information. The evidence theory is formally defined with a frame of discernment which can be represented by a finite set of mutually exclusive and exhaustive propositions, and also with a basic belief assignment measure. Two other measures characterize the evidence theory. The first one is the belief, which represents the full belief degree placed on the proposition, and the plausibility, which quantifies the amount of belief that could be given to any subset A from the frame of discernment. Thanks to the Dempster-Shafer theory, the evidential database model was born. It's formally defined as follows. An evidential database, denoted EDP, is a database that stores both perfect and imperfect information. Each attribute I in the line G from the evidential database is a normalized BBA. As you can see on my screen, the table diagnosis illustrates an example of an evidential database. We have 4 attributes. The attribute ID and patient name represent perfect information, and the attributes disease and blood type stored imperfect information. For example, the attribute disease for the first patient stores probabilistic value, since the focal elements are singleton. We have also perfect value when the focal element is singleton and its mass is equal to 1. We have the complete ignorance to represent missing information, possibilistic value when the focal elements are nested, and finally the general case where we can store evidential value. We also define the item in the evidential database which represent a focal element. An item set X is a conjunction of items that don't share the same domain. For example, from the previous table, we can see that Corona and AB are 2 items, and Corona A is a valid item set. So, an evidential association rule R is an expression in the form X implies Y, with the intersection between X and Y is an empty set. For example, we can say Corona implies I is a valid association rule if it satisfies the support and confidence thresholds. Now we move to introduce our problem statement. So the classification rules can be formally defined as a set of rules in the form of AI implies YI, where AI is the antecedent of the rule, also called the precondition, and YI is the consequent of the rule. In this case, it represents the class label. When dealing with the problem of rule-based classification, the challenges can be summarized in 3 major points. treating conflicting and redundant rules, pruning non-interesting rules, and finally, how to select the rules that cover the instance and how to combine them to decide the class label. In this context, we introduced our approach called EVRC, that stands for Evidential Rule-Based Classification. This later involves 3 steps. The first one is classification rule extraction, the second is the classifier building, and finally the rule selection and the final decision. So to extract classification rules, we start first with mining association rule from Evidential database, and we keep only those satisfying the given support and confidence thresholds. Then we preserve the set of rules whose consequent parts are a class label. For example, suppose we have the set of association rules are A1 implies C2, theta A B2 implies C1, and E1 implies B2. We have also the domain of the attribute theta C, which is C1, C2, and C3. So at the end of this stage, our classification rules or classification set of rules will be A1 implies C2, theta A B2 implies C1. The next step consists of building the classifier. Indeed, in order to build an accurate classifier, 2 pruning levels were used in this method. In the first one, we prune irrelevant rules based on the pessimistic error rate and the lift measures. Then we remove redundant rules as follows. So in the first step, we rank rules according to their confidence, support, and generality. And finally, we keep only general and high confidence rules. As example, suppose we have 3 rules. A1 implies C2 with a confidence equal to 0.5. Theta A B2 implies C1 with a confidence equal to 0.7. And E1 B1 implies C1 with a confidence equal to 0.4. So when removing redundant rule, only we keep the first and the second one, because the antecedent of the first rule is a subset of the antecedent of the third rule, and also the confidence of R1 is higher than the confidence of R3. So we keep only the first 2 rules in our case. And here come one of the most important tasks, the rule selection. So we select a subset of rules matching the given instance. The selection criteria will be the following. For a given instance X, we extract the rules whose antecedent parts have non-null intersection with X. So we continue with an illustrative example. We have on the left side of the screen 5 rules, and on the right side we have the instance under classification. Indeed, for each rule we test whether its antecedent part have non-null intersection with X, which is the case for all rules except R5. So this rule will be removed from our classification set. Now, for each retrieved rule, we compute a discount factor. It measures the relevance of the rule's precondition with the instance to classify. It's calculated as follows. For each element from the rule's antecedent, we compute a distance measure with the appropriate attribute. So, for example, for the first element, A1, we compute its distance with the attribute A. For the element B1, we compute its distance with the attribute B. So, let's take an example. So, to calculate the distance of A1 compared to the attribute A, we proceed as follows. For each focal element from the attribute A, we calculate the size of its intersection with A1 divided by the size of its union with A1 multiplied by the mass of the focal element. For example, we have A1 intersect A1, the result is A1, so the size is 1, and A1 union A1, the result is A1, so its size is also equal to 1, so we have 1 divided by 1, and the mass of the focal element A1 is 0.6, so multiplied by 0.6. We do the same for the second focal element. We have A2 intersect A1, the result is the empty set, so its size is equal to 0. We have here 0. Then for theta A and A1, the intersection is A1, so its size is equal to 1. The union is theta A, which is its size is equal to 2. So we have 1 divided by 2, and the mass of theta A is equal to 0.2. So we have 1 divided by 2 multiplied by 0.2. So the result will be equal to 0.7. And we do the same for the attribute B. Finally, the discount factor is obtained by the product of all distances. Here in our case would be equal to the distance of A multiplied by the distance of B. It will be equal to 0.7 multiplied by 0.7, which equals 0.49. Now each rule will be transformed into a normalized BBA with 3 focal elements as follows. The first focal element will be the consequent of the rule, which represents the class label. Its mass value will be equal to the discount factor multiplied by the confidence of the rule. The second one will be the domain of the class attribute, but we exclude the consequent part of the rule, and its mass value will be equal to the discount factor multiplied by 1 minus the confidence of the rule. And finally, the last focal element will be theta C, where C is the class attribute. So following the same example, we obtained the mass of D1 equal to 0.29, the mass of D2 equal to 0.2, and finally the mass of theta D will be equal to 0.51. Finally, we fuse all the obtained BBAs following the Dempster rule of combination. And the final step in our process is to decide the class level of the given instance. For this reason, we calculate the pignostic probability of each item from the domain of the class attribute. In our case, we have 2 elements, D1 and D2. So we calculate the pignostic probability of D1, which will be equal to 0.338, and the pignostic probability of D2, which will be equal to 0.662. So our final decision will be D2, which means that the class label of the given instance X is D2. To assess the performance of our proposed method, several experiments were conducted. We used 4 well-known datasets from the UCI benchmark repository. However, these datasets contain perfect information, so we need to introduce uncertainty to these datasets. To do so, for each feature we introduce partial ignorance at a degree denoted U. For example, suppose the value of the attribute A is equal to A1 and U equal to 20%. So after transformation, we obtained the following BBA: A1 with a mass value equal to 0.8 and theta A with a mass value equal to 0.2. To perform the different experiments, we deal with a commonly used technique known as the B-fold cross-validation, also known as the key-fold cross-validation. In this setting, the B is fixed to 5, which means that each dataset is divided into 5 parts. 80% of the data will be used as a training set, and the 20% will be used as a test set. Our method will be compared to the EVAC generic, EVAC precise, and TS-ARM. In each experiment, the support and confidence thresholds are respectively fixed to 20% and 50%, and the uncertainty degree is varied from 0% to 30%. As you can see in my screen, VRC outperforms the other classification methods for the balance scale and iris datasets, as you can see here. So these results confirm the importance of the pruning phase and also the group selection strategy we employed, which contribute to improve the classification accuracy. Also, the Titanic dataset confirms the previous results. However, the database vertebral revealed a weird behavior of our method compared to the others. It may be related to the number of features described in the dataset or even the features domain. Of course, we need to mention that the comparison in these experimentations were based on the accuracy of the classifiers. So to conclude this work, we tackled in this research the problem of multi-rules based classification for evidential data. We introduced a new measure to evaluate the relevance of a rule, and also we introduced a new method denoted AVRC for multi-rules based classifications. As for the research, we intend to improve the rule pruning by considering further interestingness measures. And also we want to evaluate the effectiveness of the IVRC when the class label presents imperfect information. Finally, these are some references used in our work, and thanks for your attention.